Today, we are going to train the new beginners, the virtuoso, the pre-sim and post-sim. Next page. Next. So this is the spec we are going to follow. Some of you may have done some simulation, but we are going to go through again. So this is the supply voltage, the rail-to-rail voltage. And this is the gain requirement, gain bandwidth requirement, slew rate requirement, phase margin requirement, input common mode, range, and the power dissipation. And this is the load capacitance. We have 6 electrical engineers and 2 mechanical engineers. The 2 mechanical, they are not going to do this. But I will assign them other things to do. Next page. Okay, so we have 2 OP, differential input, and the second OP, 2-stage OP, we get V out. And RZ, you need to decide, and CC also, you need to decide to fulfill the specifications. Next. Okay, so we have A1, A2, and this is supply voltage. And so this is RZ. We use the triad operation of MOS for RZ, and this is CC, the compensation capacitance. Okay. And also RB, we need to decide RB to fulfill our requirement. Next. So see, for A1, this is differential pair, so we can just consider half. And A1 equal to minus GM2. And this is output voltage. If you look at from this point, so this one, we have RO2, and for this one, we have RO4. They are in parallel. So this is A1. And I12, so this is I12. This is the current. So VA, early voltage divided by I, we can get R. Early voltage divided by I, we get R. So for A2, the GM7 and output resistance, we have, if you look at to this one, we have RO6, and this one we have RO7. So the same, we have A1, A2. And the total amplification, AV equal to A1, A2. So you can get this one by hand. Okay, next. And frequency response. We need to consider the capacitance. So this C, we can use Miller theorem. So we can put this one. Think we have a capacitance here, another capacitance here. And for this one, at this node, is CC1 minus 1 minus amplification ratio. So minus minus, we get plus. And we can, because A2 much greater than 1, so we can get the result. So for A2, we got this one. See, minus A2, so we have 1 minus A2. So this is minus, we can get plus. For first stage, this one, A1. And V in, we have V in here. So for V in, and V1 is the output, this node. So V1 divided by V in is the A1 gain. So we got this one already. And Z out 1, we have, so at this node, we have RDS2, RDS1. So this one, you can take RDS4, RDS2, RDS4. This can be taken by 4. We have this one, and the parallel capacitance. So we have these 3 in parallel. And this one, much greater than. So this one, they are in parallel. So we can take this one, just use approximation. So the total overall gain is V out divided by V in. And A2 here, A1 this one. And the other one is approximated by this one, so we can get this one. So A2 cancel out, we can get total voltage gain here. And the unit gain frequency, if the gain equal to 1, then we can calculate the unit gain frequency. See, if this is equal to 1, S equal to J omega. So this equal to 1. So you can calculate omega, unit gain frequency. Okay. Kaiser, any problem? Why we have this one, Kaiser? Can you explain how we got this one?
We will use Miller's theorem.
So which one? In this circuit?
Yeah.
CEQ at which node?
CEQ at this.
Which node?
In this one.
Okay.
This one.
Which one?
This one.
Which one? Which node? NODE?
Not this one.
Okay, go back. And what is, Kumia, what is unit gain frequency?
We take it from here, S is equal to J omega. So omega U is the gain of the circuit and the capacitance.
So which equation do we use to derive this one?
S is equal to J omega.
Which equation?
GM1 to SCC.
I mean, what is the out one?
Total Z from one step for differential circuit.
So, I mean, okay, explain this equation. 解释为什么 ZR 是这3个病。
因为 V1 在这边，然后从这边看进去的主杠是这个病原，第一说，
这应该是4啊。
对，就是这个病原这个，然后这里有一个 C，
那个 C 怎么来的？
有这个的那个米勒效应 S C 分之一。
Okay, thank you. Okay, next page. So, unit gain frequency omega AV equal to 1, we can derive unit gain frequency. And GM1 or 2, this is the equation, mu n C arcs. S is omega W divided by L, width divided by length. And this is overdrive, VOV. So if overdrive fixed, if this is fixed, we can adjust S1, 2, and CC to adjust for this unit gain GB value, unit gain frequency. So in this design, we play with S value and C value to reach our goal. Next. Okay, slew rate. See, if we have input V in, we can see how quick the output can catch up with the input. So that is the slew rate. Next page. Next. Okay, previous. So this is input, this is time, and the output. It may take a while for output to catch up with the input. So the slope here is the slew rate for the output signal to reach the final value. So the slew rate, see dV out dt, and we take the maximum value. And the slew rate depends on the capacitance we charge and discharge the capacitance. You can take, because for capacitor Q equal to CV and Q equal to I divided by T, current, I times T, charge equal to current times time, CV. So you want to get dV dt, dV dt equal to I divided by C. So I divided by C is the slew rate. And the maximum, we want to consider the maximum value. So ICC maximum is the supply ISS. See this one, ISS, the supply current. So because IS equal to 2ID1, this is ID1, and ID1 and ID2 are equal. So IS equal IS equal to I1 plus I2. So IS equal to 2ID1. So this is the slew rate we can calculate. And also we have this equation, unit gain frequency, we got this value. So we can plug CC value equal to GM1 divided by CC. So you can plug CC value. You can get this equation and plug in GM1 equation, ID1 omega U. So this is the final result, because overdrive 1 equal to this one. Kaiser, do you follow me so far? You need to derive each equation in your report, because this class, Kumel and Kaiser will write the report. Juan, yeah, please read these two sentences.
The only way of improving the through rate of the two-stage rate is to increase VD1, omega U, or both.
See, we want to increase slew rate because we want the VR to catch the input. So in order to increase the slew rate, see, based on this equation, either we increase omega U, unit gain frequency, or we increase VOD1 in order to increase the slew rate. So this is very important because mathematics is important because it will give you how the method to adjust your circuit to reach your goal. You cannot just play with spice to adjust numbers and try to get your answer. Again, do you follow me? Mathematics, mathematics, mathematics. You need to know the simple equations before you play with your spice simulation. All these equations based on approximations. So you need to understand how to make approximations of your circuit in order to get the simple equations to help you to design your circuit. So this is why these equations are important. For your own circuit, you also need to derive some simple equations to help you to play with your design. Next page. We have internal slew rate. This is internal slew rate. We have external slew rate, depends on this one, C2. So again, this is external, connect to output. This is internal, inside the circuit. For external slew rate, again, we use I divided by C. C2 value here, and IO2, this one. And IO2 equal to I6 minus IX, ID6 minus IX. And IX maximum is ISS, the current. So this is the equation for external slew rate. Kaiser, please. Okay, explain this equation.
This is slew rate in external.
Explain.
This is external slew rate ratio for IO2 and C2, and this is internal slew rate.
Explain the equation.
Here ID6 is the current from here, and ID maximum is here, and ID maximum is equal to ISS, supply current, source current.
Okay, thank you. Next page. Now, frequency response is important for circuit design. In order to derive the frequency response, we use this small signal equivalence. So this is A1. We have A2 here. For A1, see GM1 V in. This is the voltage source. We have R1, C1 at node V1. This is node V1. And we have RZ and CC. Or previous. See, we have RZ and CC here. We have V1. So this is V1. V1, GM7, we have a current, voltage controlled current source. Okay, next. See, V1, we have CC and RZ. And at node 1, we have the R1 and equivalence capacitance. So this is for GM7 V1. This is output R2 and C2 at node V2. Kumel, explain why C1 equal to these three values. C1, previous. Okay, why we have those three C1? Can you go to next? Can you copy this equation? Yes. Passed. Okay. Explain why C1 equal to those three capacitances.
C1 is total capacitance. C dB2.
Go later to draw dB2, dB4, and GS7. Draw them.
Which circuit I have to draw?
Huh? Bottom. Okay, go back. I will ask Bottom to draw CDB2, CDB4, and CGS7 on the circuit. Yeah, just draw. Okay. Okay. So, next one. Next page. Next. Again. Draw this one. Copy this one. Previous. Okay, again. Draw C2. Okay, thank you. Next. So this is a small signal model. Using this model, we assume we want to simplify our equation. Remember, always we start approximation. We make everything simple first. So we take RZ equals 0, no RZ. Then derive V out divided by V in. Using this circuit model, we can get this one. So now, everyone get a A4 paper and derive this one. And mechanical engineer, you don't need to do that. You can just watch them do that. But if you want to practice, it's up to you. Okay, camera off. Okay, you are required to derive these equations in your report. Next page. The denominator can be simplified to this 1 plus b1s plus b2s squared. Then they can be factored out using this equation. Assume P1 is the dominant pole, means P2 is far away from P1. So high frequency P2. P1 is low frequency. So P1 is the dominant pole. Because P2 is very large. So S plus omega P1 plus S divided by omega P2. Because omega P2 is very large, so we can ignore S plus S divided by omega P2. So we are left with this one. So omega P1 will be 1 over B1. So this is, we can use this method to get approximate value of the dominant pole. And remember, omega P1, omega P2, omega P1 times omega P2 will be 1 over B2. So if you know omega P1 value, so omega P1 equal to 1 over B1. So if you know B1, this value, then we can calculate omega P2. So this is omega P2. You are required to derive omega P1, omega P2. Then this one is the 0. So 0 is previous. So V out divided by V in. So this is, we have 2 poles here. We have 1, 0 here. So use this equation, S equal to omega Z. We can get, next page, can get this solution. So under these conditions, we can simplify omega P1 and omega P2. These are the simplified equation. You need to convince yourself under these conditions, they can be simplified. For design purpose, there are too many variables. You cannot get very direct sense. But if you simplify your equations, you can get this simple equation and this simple equation. So using them, easier to help you to know the location of P1 and P2. Always simplify. Otherwise, you have no way to know the effect of each parameter on your system. Next page. Okay. So load compensation. Remember, we have RZ. We ignore RZ in the previous, but now we want to consider RZ. RZ previous. See, omega Z equal to this one. And next page. See, GN7. We assume no RZ, and GN7 is here. GN7 divided by CC minus previous. See, minus GN7 divided by CC. You can move this one become 1 over GM7. Previous. Okay, next. See this one. Okay, sorry, previous. See GM7 and RZ here. So you want to consider RZ. RZ is the resistance. If you look at from this point, so here, at this node, you look into this transistor, you can see the input resistance is 1 over GM7. And this one, RZ, they are in parallel. Sorry. Next. So RZ here, and this is V2. So you look to the ground. So this one, if there's a 1 over GM7 is the input resistance, and RZ. So if you see, V1 and look to the ground, RZ and this one are in series. V1 look to the ground. So next one. So that's why sorry for this one. Okay, previous. For this small signal analysis, you put RZ back. You need to run through. It's not easy to tell, but you need to run through the small signal analysis. Next, to get this value. So if we take RZ equal to 1 over GM7, then this one disappears. But if RZ much greater than this one, RZ greater than this one, we move the right-hand side 0 to the left-hand side. RZ greater than this one, minus become plus. So we move this right half plane 0 to the other plane. Remember, 0 and pole can be cancelled out. So we want to cancel out omega P2. So if we take this value, much greater than this one, and the location of 0 and pole are very close, we can cancel omega P2. So but C2, because if you put CC back here, CC value C2, okay, previous. Okay, C2 here. So it's the combination of dB7, dB6, and CL2. But usually C2 value is not known. So next one. He says C2 is not known, so we are not easy to use this equation. Okay, Agan, could you read this one?
Choose RZ even larger to move the left half plane to the frequency signal greater than mu t.
Omega t.
Omega t.
So we take omega omega t equal to 1.2 omega u, the unit load frequency. And omega z1 prime we can approximate the RZ value into this value. Okay, next. So another way to find omega z. So this equation, see, because V out so this is another small signal model. Remember, omega z is the 0 position. For you want to get 0, V out divided by V in, previous. See, V out divided by V in. If you want to get the value of the 0, they need to be equal to 0. So the denominator is 0. If this is 0, means V out must be 0. Next. So if V out is 0, then all the current goes there, must go out. V out 0. So no current goes through R2 and C2. And all current goes from this way. So V1, node voltage, this is 0. Divided by impedance, RZ plus the impedance, this one. So this is the current, goes through this way, must go out. So this current is UM7V1. So using this equation, you can calculate S equal to omega Z. So we can calculate omega Z using this simulation. So in your report, you will go through all the derivation by yourself. 4 students are required. Actually, 1 year ago, I didn't ask Bo Chen and Argan to give me the pre-training report. And you didn't derive all the equations. So I will require this report from the 6th electrical engineer, the due date next Thursday. You have 1 week to prepare this pre-training report. Okay, next one. This is the supply voltage, the bias. They depends on temperature and process. So we want to make your supply independent of temperature. So in the end, if you can do this, see, omega divided by L, omega divided by L. If they increase together, so the temperature effect will be canceled out. See, we only have omega L, WL, WL, WL. If there's a temperature, they will become long together, they will become short together for the W and L. So if you do this, in the end, you will derive this one, means your device is temperature independent. So now we want to select RZ. So you select RZ. If you decide GM7, you can use this equation to determine your RZ, to compensate for temperature. So we use the triad region, MOS 16. So this is RDX16, this is the equation. And GM7, this is GM7 equation. So you multiply these two. The purpose is to get them constant. And VA, VB, this is VA, VB. You make VA equal to VB. So you can get overdrive 13 and 7. VA, VB the same. So VOD 7, overdrive 7, 13, 7. So VOD 7, this one, VOD 13, this one. You can manipulate the equation. And we have this condition, and you can eventually derive this one. Actually, I have laid out all the equations, but you need to just do the mathematics. Just carry out, derive all this, just practice by yourself. Then in the end, you will get this one. I mean, read this second.
Make GM7 independent of passive and temperature.
Yes. See, if you use during the CMOS fabrication process, we have the photo mask. If there is an alignment error, we will make the same error for all of them. So the alignment error, they will cancel out each other. So for process error, eliminate, and temperature, heat expansion, or cold shrinkage, they will expand and shrink all together. So we can avoid temperature dependence. Okay, do you understand? Next. Then phase margin for stability. So this is our AV, the transfer function or the gain of our system. So the phase margin equal to 180 degree plus the phase when AV equal to 1. When this one equal to 1, the phase. So the phase for this one, so 180, 180. And for this one, for this pole, we have minus arctangent. For this pole, we have minus arctangent. And for this one, 1 minus omega. So we have the minus sign, and arctangent. This is the gain, this is the frequency when gain equal to 1. So GB is the frequency when gain equal to 1. And we take gain bandwidth much larger than omega P1. So gain bandwidth much larger than omega P1. So this one, if this one is very large, means arctangent, this one is pi over 2, 90 degree. And put this one here, and this one here. See, remember when AV equal to 1, omega equal to GB, omega equal to GB, when AVS equal to 1. This is unit gain bandwidth. So this is the phase margin equation. So after you design your device, you need to check your phase margin. So you have the gain bandwidth requirement. You have so you need to ensure the phase margin greater than 65 degree. Next, input common mode range. So this is input common mode range. So SD5, see, input common mode, this is input. So the maximum, this one, VDD minus VSD5 saturation. VDD minus VSD5 will be the top of your input common mode. And your minimum, see, look at VSS here, VGS3 here. And this is threshold voltage. So we have the minimum value and maximum value. So this is your input common mode range. Next, and output stream. This is output. output. See the maximum VDD minus VOV6. VOV6. So we have the maximum output and the minimum output VSS plus VOV7. So this is the output stream of your two-stage. Next page. This is your bias stage, this one. Now you need to determine RB. Next. See, this is the RB equation. So follow this current, ID 15, ID 13, and this relation, overdrive GS, and plug in all the equation here. You can derive this final solution. Kumel, read this.
GM13 is determined by geometric ratios only, independent of power supply voltage, process parameters, pressure, or any other parameter with large variability.
See, GM13 only depends on geometry. You should be happy. Only geometry ratio only. No power supply voltage. No process parameters. Temperature. Okay, next page. So input offset. I3 and I4. I3 and I4. So we require DS3, and DS4. We require the same. Then if we have this one, you can be sure I3 equal I4, because this is what we want. I3 must be equal to I4. So using this one, you can derive your final condition. You need to select X7 equal to 2, X4, X6 divided by X5. You need to have this one, because we want to get I3 equal to I4. So if I3 is not equal to I4, you have input offset. We don't want input offset. So this is the requirement we need to have. Next page. Common mode rejection ratio, CMRR. So ADN divided by ACN. This is the definition of ADN, definition of ACN. So you need to use SPICE to calculate this one. And this is power supply rejection ratio. Power supply, ADN. Okay, so this is the equation you need to use. Next. So in this circuit design, you need to decide mu n and mu p first. So from the SPICE LIS, you can get beta value. And beta divided by omega L is the mu n Cx and mu p Cx. These two values, you can use your SPICE and the U18 technology. You need to find out these two values. So that's the first step. You need these two. Do you understand? Next. Then, based on the phase margin requirement, 65 degrees, then we need to decide the CC value. See, using this equation, 65. And the CC value is this one. So 25 here. 90 minus 65 equal to 25. So you can get CC value, 0.22 picofarad. But we select CC because CC must be greater than this value. So we select 0.0 picofarad for our design. We require omega z greater than 10 GB. Remember, we want omega z very large. So omega z equal to this value. 10 GB, this is 10, this is GB. So your CC also need to satisfy this condition. Okay, so this is next one. Slew rate. The slew rate I5 CC. Remember I5 is ISS. And slew rate 30 volt per microsecond. Remember we select CC 0.3 picofarad. So using this equation, you can get your I5 value. CC is this one. And we just pick some number here. Okay, next page. Then this is the procedure to decide S1, X6, 10 to 11. You can follow the argument. Okay, next. So after that is the SPICE simulation. So next Thursday, at the beginning of the class, you need to SPICE simulation. Next, slew rate simulation. Next, ICMR simulation. Next. So I have put all the contents you need in your report. These are all the contents, all the requirements. Next, settling time. So you need to calculate your own result. Rising settling and falling settling time. Next, CMR. So you need to calculate your CMRR value. Next, PSRR. Okay, next. See previous. For PSR plus, we have 1 volt AC here. Next page. For PSR minus, we have 1 volt AC connected here. We take 0.5 volt as the input. Half of the 1.8 volt. Okay, so you need to calculate your PSRR plus and PSRR minus. Next, offset. So output offset and input offset. So this is suppose if they are the same, you shouldn't have any Vout. But in reality, we have Vout offset. So we just use, if you take this one is 0.9, and you need to adjust this one to make Vout the same as. So this is a perfect condition. If you use this one, your circuit will give you some curve. But after that, you need to change this one. and you fix this one, you change this one, you can get some value. And this value need to fit to your previous curve. In that case, in order to calculate the offset. Next one. Output swing. Okay, follow the steps anyway. Next. So you can do your pre-simulation. After pre-simulation, draw the layout and do the post-simulation. Next. And this is the table you need to have, the corner. Okay, this is what required next Thursday. So you need to follow them and create your Word file report. Derive all the equations in your Word report. So this training is necessary. And all of you should do this, must do this. Okay, any problem? Okay, very good. I'm really excited to look forward to your report. Okay, that's the end of today's class. Bye-bye. Camera off.